Hello, dear children. I'm going to show you how to construct things called resonance structures with Lewis structures and also calculating formal charge. At this point, you should be able to draw Lewis structures for compounds that have follow the octet rule, for compounds that expand their octets, and also determine if a molecule is polar or not, which we haven't really done shapes yet, so that's kind of a question at this point. By the end of this lesson, you'll be able to draw Lewis structures for compounds that have resonance structures, and also use formal charge to determine which resonance structure is favorable. We'll also look at determining bond order, which takes like 12 seconds. To introduce this concept of resonance, I'm going to draw the Lewis structure for the nitrate ion. So we think about the process here. We look at valence electrons. Nitrogen has 1, each oxygen has 6, so that's 18, plus 1 more because the nitrate ion has a negative charge. So we need to show 24 electrons in this picture. So when you start to put this together, you always start by single bonding the elements until you complete octets, and if you need more electrons, you try double bonding it. And what you find with the nitrate ion is that you need to have one double bond, and the other 2 bonds between the nitrogens and the oxygens are single. Now the issue that arises is like which oxygen gets the double bond and which oxygens get the single bond, and is there any favoritism towards one structure over the other? And there's not. So if you come up with a structure where you can have a double bond like floating around in various locations, and none of them are favorable over the other, this is called resonance. There's no reason to pick one of these oxygens over the other to make the double bond. They're all exactly the same. They have the same number of valence electrons. They all can bond to nitrogen in the same way. So the way that you would represent this in a structure is you would draw each of your possible resonance structures, and then you would put a double-headed arrow in between each of the resonance structures. This is not saying that they're going through some sort of equilibrium or there's a change. It just means that they can all exist. And when these structures are actually studied by chemists, what they find is that the bond lengths of the 3 sites are not short for the double and then longer for the 2 singles. It's actually kind of a blending between a single and a double bond. So what they actually find for the bond length is that each of these 3 bonds is equivalent to 1.3 bond lengths. Not a single, not a double, but since we're dividing that into that double bond into thirds, it's kind of like 1.3 bond lengths for each. So the reason why resonance structures come about is because sometimes you have more than one valid Lewis structure that can be written for a molecule. The resulting structure of the molecule in reality is given by an average of the resonance structures that you can make. So the electrons are going to float around, but the nuclei are going to stay put. So the shape stays what the shape should be. It's just that the electrons are kind of floating. So we represent this by double-headed arrows, meaning that the structures are all equal to one another, not that they're changing from one into the other. So this resonance concept is used to... and we're back. It's used to fix the localized electron model. The localized electron model says these electrons are in this bond between these 2 atoms, period, end of discussion, they're not moving. But what actually happens is electrons are delocalized. They are not just going to stay associated with one particular pair of atoms bonded together. The electrons are able to move about the molecule. Okay, this is kind of repetitive. Experiments show that NO3 doesn't have any double bonds. It has all single bonds with lengths and strengths between single and double. So they're actually like they're actually 1.3. This link I actually have posted to Schoology that reviews the concept of resonance structures pretty nicely if you want a little extra. So this other one, this N2O4, the basic structure of it is outlined here, but this doesn't have all the electrons it needs to. Everyone wants to make announcements. So anyway, you have 2 nitrogens with 5 apiece, so that's 10. You have 4 oxygens with 6 apiece, so that's 24. That's where we get this total of 34 electrons. So when you start to make this structure and you put in the bonds, you've taken care of 2, 4, 6, 8, 10 electrons. So I still have 24 electrons I need to put into this structure. When you do this, when you go through the whole process of counting the electrons and counting down and completing octets, because both nitrogen and oxygen must complete octets, no more, no less, you see that you have the option of putting the double bonds on oxygens that are coming off the same side or opposite sides. Like if you could also have flipped this molecule over, it's the same thing, or flip this molecule over, it's the same thing. So there's really two resonance structures. If you did draw all four possibilities, that's fine, but really there's just two: diagonal double bonded oxygens or ones that are coming off the same side. This is actually called cis and trans conformations of the molecules. The next example I'm going to show you is for ozone. If you go through ozone, you need to show 18 valence electrons in total. So when you put it together, you find, all right, well, I can do that by bonding a double on one side and a single on the other side. I can't divide it up any other way. The true structure of ozone, though, we do have bond lengths between that single and double and in the form of resonance. So we would use resonance structures, or just a double-headed arrow, use resonance structures to show ozone molecules. Oh, look, I blended colors. So you should have some idea of what a resonance structure is at this point. At least you'll have an idea when we get to practice on some in class. The other thing that can involve resonance is this concept of formal charge. And this happens especially when you're dealing with molecules exceeding the octet rule, and then their resonance structures are very different, that they can have different numbers of single, double, or triple bonds. So there is a way to actually determine the best structure. So you can have resonance, but then also by doing this calculation of something called formal charge, you can figure out which of the resonance structures is actually the most favorable. The way that you calculate formal charge, you need to remember this, is the formal charge on a particular atom is the number of valence electrons of that atom minus the number of bonds it has around it minus the number of dots it has around it. So V minus B minus D will give you formal charge. Again, this link is posted to YouTube that explains it as well. So the three things, again, you need to know are the number of valence electrons of that particular atom, how many bonds you drew around it when you made the Lewis structure, and how many dots you drew around it for lone electrons. So here we have two possible structures of the sulfate ion. That should be in brackets. And it asks which one is better and why. So what you would do here is calculate the formal charge on the sulfur and each of the oxygens. So again, formal charge is equal to the number of valence electrons minus the number of bonds around that atom minus the number of dots it has. So looking first at the sulfur, sulfur has 6 valence electrons minus, well, how many bonds do we have around this sulfur? We have 2, 4, 6, 8 bonds. So minus 8. I'm sorry, no, you want to count the actual bonds, not the number of electrons. My bad. Where did I get 8 anyway? So you want to count the number of actual bonds. So 1, 2, 3, 4, 5, 6 bonds, and there's no dots around it. So the formal charge on the sulfur is 0. And then we want to look at each of the oxygens. So let me erase that. So the oxygen, let's start with the red oxygen at the top. Oxygen starts with 6 valence electrons. How many bonds does it have? 2. How many dots does it have? 4. So formal charge on that oxygen is 0. That's why it's written next to it. The oxygen to the right, that bluish color, 6 minus 2 minus 4 is also 0. The oxygen at the bottom, the purple, 6 minus 1 minus how many dots? 6 gives me -1 for that formal charge. And then the oxygen on the left, which is bonded in the exact same way, would also have a -1 for the formal charge. The other one that we have here, where we have single bonds around all of the to all of the oxygens, sulfur has 6 valence electrons minus 4 bonds minus 0 dots gives me a +2. And then each of the oxygens, since they're bonded identically, would all have the same formal charge, 6 minus 1 bond minus 6 dots, which is -1. When you want to determine which one has the best, is the best conformation, you want the total to be as close to 0 as possible of all of your formal charges. And you also want the element that has the highest electronegativity to have a charge, the highest formal charge. Okay, so the goal for molecules is to get formal charges as close to 0 as possible. The sum of all the formal charges on that molecular ion must equal the overall charge of the species. So if you add up all the formal charges for the sulfate ions, it has to add up to -2. If you add up all the formal charges on a particular molecule, it has to add up to 0 because molecules are neutral. The best structures are one that obey the octet. If you have to expand the octet, it's fine, but it's usually not going to be super favorable. So you want the fewest charges listed possible, and I said the most positive formal charge and on the lowest electronegativity. You want the most negative on the most electronegative. So that just gives you another example of formal charge. So for nitrogen, it would be 5 minus 1 minus 6, which is -2. For carbon, it would be 4 minus 0 equals 0. And for oxygen, it would be 6 minus 3 minus 2, which is +1. If you add all these together, you do get -1. So you do get a -1, which is the charge of that polyatomic ion. The next example, we have 5 minus 2 minus 4, which is -1. Here we have 4 minus 0, which is 0. And here we have 6 minus 2 minus 4, which is 0. So add all those up, you do get -1 for the overall. And then the last one, we have 5 minus 3 minus 2, which is 0. Here we have 4 minus 0, which is 0. And here we have 6 minus 1 minus 6, which is -1. Add all those up, you do get a -1 charge. Now, the reason why this last one is the most favorable is because it has the negative formal charge on the most electronegative element. So of those three, if you think about trends, they're all in the same period. As you go to the right, the electronegativity increases. So here, for these practice, we do have two different examples. So the xenon trioxide, we can do these are all different resonance structures that are possible. They all have the proper number of electrons. So we just have to look and see which one is the best based on formal charge. So for xenon, for the first structure, xenon has 8, minus 3 bonds, minus 2 dots, which is +3. Then we have all three oxygens are exactly the same. So 6 minus 1 minus 6 equals -1 for all three of them. So that's a total of -3. So when you add all those up, it adds up to 0. It's a molecule, it doesn't have a charge, so that makes sense. Also, the oxygen has the most negative formal charge, and oxygen has the highest electronegativity. For the next example, for xenon, 8 valence electrons minus 4 bonds minus 2 dots is +2. And now we have 2 oxygens with the same bonding structure, and we have 1 oxygen that's different. So the single bonded oxygen, we have 6 minus 1 minus 6, which is -1. And then for the double bonded oxygen, we have 6 minus 2 minus 4, which is equal to 0. So if you add all those up, there are 2 of those, you do get added up to 0 overall. And we do have a negative formal charge on our oxygen as well. For this one, though, we have exceeded the octet for xenon. And then the last one, xenon, 8 minus 6 minus 2 is 0. And then we have oxygens, 6 minus 2 minus 4 is 0. And obviously we're doing that 3 times, so it's going to be all canceled out. So the best resonance structure is actually going to be the first one, because the first one, we have the most negative formal charge on the most electronegative element, which is oxygen. We also did not exceed octets. Okay, so you don't want, so even though like the first one and the third one, well, they're you know all symmetrical kind of in structure in terms of they're all bonded the same way with the oxygens, the fact that the xenon didn't exceed its octet in the first one makes it the most favorable structure. These two are actually going to be equivalent in terms of formal charge because all you did was flip the bonding around. So one other example here, POCl3 and assigned formal charge. So we'll do POCl, Cl, Cl, and we got to count. So 5, 6, and then 21 is 32. So we already took care of 8. So I have 24 electrons left. Oxygen must complete its octet. We can actually just go ahead and fill in octets for all of them, and that takes care of all of the electrons. So now we can do formal charge. The Cls will all have the same. So phosphorus is 5 minus 4 minus 0, which is plus 1. Oxygen would be 6 minus 1 minus 6, which is negative 1. And then each chlorine is going to be 7 minus 1 minus 6, which is 0. So did I do all of my formal charges add up to 0 because this is a molecule? Yes. Do I have the most negative formal charge on my most electronegative element? Yes, that's oxygen. Did I exceed an octet for anybody unnecessarily? No. So this is really the only structure, and it has good formal charge. These are some other examples. I just want to do this one. The other ones we already looked at, I think. So the xenon tetroxide, so we have 8 plus 24 equals 32 electrons necessary here. So that brings us down to 24, and then we just need to complete the octet for the oxygens, and that takes care of all of our electrons. So now formal charge for xenon would be 8 minus 4 minus 0, which is plus 4. And then for each oxygen, we have 6 minus 1 minus 6, which is negative 1. And then we have 4 of them, so that's a total of negative 4. So when we add those together, we do add up to 0. That's the only possible structure. So that was to give you an overview of resonance structures and also calculating formal charge. So if you have, sometimes you only have one option for a structure, and that's fine. You could just calculate formal charge off of it. But other times, if you do have multiple structures, you would be asked to determine which one is most favorable, and for that, you would use formal charge. The last thing here is just bond order, which is super easy. The bond order just is how many bonds there are between two atoms. So a single bond would be first bond order, second, a double bond would be 2, and a triple bond would be 3. To keep in mind here is the higher the bond order, the stronger the bond's going to be, the shorter the bond's going to be. But that's really the only time you're ever going to see something about bond order. So for here, the bond order is 2. For here, 2, 2. 1, 1, 3, 1, 1, 1, 1. Like, it's real exciting. Can you count lines? Yes, you can. So I hope this gave you an overview of resonance and formal charge, and then also determining bond order. That is all. We're going to do practice with it in class. Peace out.